Okay, in this section, we're talking about section 5.5. These are the nonlinear systems of equations. So in this section, and we only do the two sections in chapter 5. Chapter 5 is about systems of equations. In the previous section, we covered 5.1. They were all lines, linear. All variables were raised to just the first power. And actually, this first equation example I have here, this is linear. X to the first, y to the first, we know that graphs to be a line. But this second equation is nonlinear. It has an x squared in it, actually going to make a parabola shape. So in this section, at least one of the equations will be nonlinear. Now, to solve a systems of equation, that means you're looking for their intersection place, the point where the two have the same solution. In nonlinear, there could be more than one of those places. So let's investigate this equation by graphing. So this first equation is a line. We could solve it for y by throwing the x across the line, and I've done so here. This first equation, x plus y is -2. We take the x across the line, and once we solve it for y, we can now plug it in our graphing calculator as y equals. Also, I'm going to do that by hand. It is a negative slope line, so it comes down this way, down 2 places. We could plot some points and look at that, but it looks something like that. Then, the second one, x squared minus y equals 4. We can solve that for y as well and put it in our graphing calculator or do it by hand, but that's what I've done here, the second equation. X squared minus y equals 4. I brought the x squared across, making it negative x squared plus 4. And then because the negative in front of the y, I had to divide by a negative on both sides to make that positive y. And both of these divided by -1 makes that x squared minus 4. That's a parabola moved down 4 places. So something like that. So we've got a parabola shape and a line. So there's actually 2 points of intersection where they cross here and here. And I may not have drawn that exactly to scale, but I want to show you that on your graphing calculator. So you can type in, let me get this. So you could type this into your graphing calculator. I know we always have that little bit of glare, sorry. So type that in, your y equals, and then we can hit graph. Oh, let's see, let me make sure I hit graph, and then look at that. So it draws the parabola red and then the line in blue, and we're looking for their intersection. So on the graphing calculator, you can hit the second of trace. It brings up some options there. The second of trace. It looks like I've already done that but for you, but normally, let me clear that out so we can see that happening. Okay. So I've got y equals, I hit graph again, second of trace brings up these options. I can go down to intersect, number 5 on the line there, intersect. It always makes you touch it on the left side somewhere to see, to bound it. Then on the right bound, enter, and then it should tell you the points of intersection. So that's how you can do it with your graphing calculator. Let me hit that again. So left bound, you can touch it on either one, the red or the blue, and it should draw that line in there. And then touch it on the right side, enter, and then it should give you that point. So it intersects at 2 places actually, and we can find those 2 points by our graphing calculator, by graphing it by hand, but then also the more reasonable way to do it, besides with the technology, and sometimes the technology does fail us whenever they're not the types of functions that we can put in our graphing calculator, we need the other methods. So there is another way to solve this, and I want to demonstrate the same equation by the addition method. So I could simply add those 2 equations together. This is what we did in the last section as well. When you add, y and minus y will cancel out, so it's already set up nicely for the addition method. X and x squared do not add together. I'm going to write that as x plus x squared, or putting it in descending order. I put the x squared plus x. But add those 2. That cancels. -2 and 4 is 2. And then what we have is a quadratic equation. So to solve this quadratic equation, we can do that by factoring or the formula. Different methods we have, you know, at this point for solving quadratics. It is factorable. You can check that out. It would FOIL back to the correct answer. We get -2 and +1. So those are both x values, notice. That's different than what we did on section 5.1. Here we have 2 values for x. So we need to find both of their y counterparts. So I plug in -2 for either one of these previous equations. Whichever one, you get the same result. So whatever looks easiest, I'm going to go to this first equation. X plus y equals -2. So if x is -2, y has to be, you might just see that, y would have to be 0. But if we go through the motions, you solve that and see when x is -2, y is 0. So that's one of our points. And you can see that looks about like what I've done here in my little sketch. At -2, 0, those two graphs intersect or share a common point. The other one, when I plug in x is 1, again to either equation, and I'm going to choose the easier one of the two, I feel like. I'm plugging x is 1 plus what equals -2. And then to solve that, y would be -3. So when x is 1, y is -3 is the other point of intersection. And that seems about reasonable there, over 1, down 3. So 2 solutions to this system of equations. All right, so the addition method can be used on these sometimes as well. The other method is substitution method. So I'm going to go through how to find those same 2 solutions with substitution. If you'll recall, the substitution method has you solve for one of your 4 variables, whichever one you think looks easiest to solve for, and then plug in what it says that variable is into the other equation. So what I've done in your notes is I've solved for y in equation 1. So I solved for this y by throwing the x across the line and wrote that as y equals -x minus 2. Now there's other ways to do this. You could have solved for any of the variables that you like. So that's just one way. Then whatever you get for y, it's saying these 2 things are equivalent, so they're substitutable. So you can plug this in for that or that in for that. So what works for us to help us move along is in the other equation, substituting this y is -x minus 2. So we plug that in for the y variable. And it's going to look like that. And then that's going to make an equation now that we can solve for. Oh, I'm looking at your notes. I think I solved for the x variable, but that's okay too. Either way, and you can see an example of solving it the other way it looks like in your notes. But either way, it works. Doing it with this method, you'd have x squared plus x plus 2 equals 4. That's another quadratic equation. I think we did one very similar to this just a little bit ago. You can solve this by factoring. It'd be x plus 2 and x minus 1. If you FOIL this together, you get the 1x in the middle. So that works. Then set each factor equal to 0. Gives you 2 solutions for x, that -2 and +1. And then just like with the other example, we have to find their counterparts. We plug in -2 for the x here or here will give you the same result. So let's say -2 plus what equals -2. We saw earlier that solves to be y is 0. So we have one solution at -2, 0. Then we do the process again, plugging 1 in for x. X is 1. So 1 plus what equals -2. And that solves to be -3. So other solution is x is 1 and y is -3. 2 points of intersection, 2 solutions. All right, so let's try another example. But that's basically the lesson solving by with nonlinears with one of the 3 methods, either graphing, and feel free to use your graphing calculator to help you locate that point of intersection, or addition or substitution. Some equations are going to lend themselves better to one method more than the other, but you can explore whichever method you prefer. All right, so here's another example. I'm kind of partial to the addition method. Usually I find that a little more user-friendly for myself, unless it's just absolutely already solved for one of the variables to use substitution. So I would do this method by addition because I'm seeing a negative y and a positive y would naturally cancel out. Very similar to one we just did. You have x squared plus x. Remember, you're adding, and that's why those cancel. Negative 4 and 6 is 2. Oh my, not this again. Is this, it is a different problem than we just worked, but was coming out with a similar answer, just a little different rearranging, but we've seen this one now a couple of times. Factoring, and then setting each part equal to 0. You get 2 answers for x. X is negative 2 and x is 1. I think we're going to have different answers for y this time, though, so not exactly the same problem, but similar. So first one, I'm going to do x is negative 2 minus what equals negative 4. So solving that equation, negative 2 minus what is negative 4 is really what it's saying. To solve it with our little method we use, you might already kind of just know what works there is positive 2. So when x is negative 2, y is positive 2. For the other one, I'm plugging in x is 1. 1 minus what is negative 4. Throw the 1 across the line. Negative y equals negative 5. Divide both sides by negative 1. Y is 5. So when x is 1, y is 5. And again, to know for sure those are truly the right answers, to check your work, you can plug those back into the original equation. Notice negative 2 minus 2 is negative 4. Negative 2 squared would be 4, plus 2 is 6. Then checking 1 and 5. 1 minus 5 is negative 4. 1 squared plus 5 is 6. Both of those check out. All right, let's look at another example. And always, I like for you to pause the video and practice these ahead of me. It helps you to be actively learning as we go. Okay, our next example, y equals 3x plus 5, and then x squared equals y minus 1. And I've requested on the handout that you solve these with substitution method, but you can really solve any of these with any method that suits you. This one's set up nicely for the substitution method, though. If you can see that, it's not rearranged in a way that addition, although I could use addition, but it's set up to where y is already solved for, y equals that, and I can just sub that in for the other y. So y is 3x plus 5, then minus 1. And then simplify that a little bit. It's a quadratic again. You're seeing a lot of quadratics here. For quadratics, we get it on one side equal to 0. And then factor that. If you still hate this factoring method, always feel free to do A, B, C in your quadratic formula to get your x solutions that way as well. This will be x minus 4, x plus 1. Set each part equal to 0. You get 2 solutions, 4 and negative 1. We need their counterparts, which we find by going back to one of the original equations. Remember, we have 2 original equations here, whichever one, but I always pick the easiest one. So I'll go to this first one. Y equals 3 times x, which is 4 now, plus 5. So y equals 17. When x is 4, y is 17. That's one of my solutions. Over here, doing negative 1, y will be 3 times negative 1 plus 5. Crunch those numbers and you get y is 2. So when x is negative 1, y is 2. Again, you can check those back in the original problems. They should both work when checked back in.